Welcome to the course CS467 Machine Learning. Myself, Meherban MS, Assistant Professor, Department of Computer Science, Rajagiri School of Engineering and Technology. In the previous video, we have discussed Module 4 Part 1, Part 2, that is Decision Tree and CART algorithm. So in this video, I am going to discuss the last portion of Module 4, that is Neural Networks. Let's see what is artificial neural network. So an artificial neural network, it is a system inspired from a biological neural network. So it's a model, the relationship between a set of input signal and an output signal using a model derived from our understanding of how a biological brain responds to stimuli from the sensory input. That is, it is a system which is equivalent to a human brain. So brain uses a network of interconnected cells called neurons to create a massive parallel processor. So similarly, the ANN uses a network of artificial neurons or nodes to solve the learning problems. So let's see how our biological neural network will work. So the different parts are axon terminal, then dendrite and the cell body. So in the cell, the incoming signal are received by the cell's dendrite through a biochemical process. As the cell body begins accumulating the incoming signal, a threshold is reached at which the cell fires and the output signal is transmitted via an electrochemical process down the axon. At the axon terminals, the electric signal is again processed as the chemical signal to be passed to the neighboring neurons across a tiny gap known as a synapse. Human brain has an interconnected network of approximately 10 raised to 11 neurons, each connected on an average to 10 raised to 4 other neurons. Even though the neuron switching speeds are much slower than the computer switching speeds, we are able to take a complex decision relatively quickly. Because of this, it is believed that the information processing capabilities of biological neural system is a consequence of the ability of such systems to carry out a huge number of parallel processes distributed over many neurons. The developments in ANN system are motivated by the desire to implement this kind of highly parallel computation using distributed representations. What is artificial neurons? An artificial neuron is a mathematical function conceived as a model of a biological neuron. Artificial neurons are elementary units in an artificial neural network. The artificial neuron receives one or more inputs and sums them to produce an output. Each input is separately weighted and the sum is passed to a function known as an activation function or transfer function. An additional parameter bias is used to adjust the output along with the weighted sum of the inputs to the neuron. Bias values allow you to shift the activation function to either right or left. So bias can be positive as well as negative. So in this slide, this is a simple architecture of artificial neural network. Here you can see x0, x1, x2, xn are the different inputs and w0, w1, w2, wn are the weights, and we have to calculate the summation of the input multiplied with the weight. And the next one is an f, that is an activation function. We have to apply activation function which will produce the output. Then finally the y value, which we have to apply the function over the net input, which is multiplied by weight value. So let's see the notation. x1, x2, xn be the input signals, w1, w2, wn is the weight associated with input signal, x0 is the input signal taking the constant value 1, that is we can treat it as a bias, and w0 is weight associated with x0 called the bias value, and the sigma, which is indicate the summation of input signal, and f is the function which produce the output, and y is the output signal. So this is a simple architecture. We have input and we have different connections that is connected by a weight. Then finally we have to calculate the weight multiplied with the input value. Then we have to apply an activation function over this net input. So that is your output value. So in this slide, let's see what is the difference between biological neural network and artificial neural network based on the representation. So in the slide, you can see the different parts in biological neural network as dendrite, cell body, nucleus, axon and axon terminals. So for the dendrites, it's act like an input and there will be a nucleus and the cell body. So it act like a bias value and you can see the axon that is equivalent to the output in artificial neural network. Let's see what is meant by activation function. In an artificial neural network, the function which takes the incoming signals as input and produces the output signal is known as the activation function. Activation function decides whether a neuron should be activated or not by calculating the weighted sum and further adding bias with it. So the purpose of the activation function is to introduce non-linearity into the output of the neuron. The activation function does the nonlinear transformation to the input, making it is capable to learn and perform more complex tasks. So there are different type of activation functions we'll discuss in the coming slide. So let's see the first activation function, which is called threshold activation function, which is calculated if x is greater than 0, the value which is 1, and if is x less than or equal to 0, then it is equal to -1. The next activation function is unit step function. So unit step function, the value is quite different from that threshold activation function. Here it is if x is greater than or equal to 0, the value is 1. If x is less than 0, the value is equal to 0. So let's see the graph of unit step function. The next function is very important function that is called sigmoid function, one of the most commonly used activation function, which is also called as binary sigmoid or logistic sigmoid. The standard equation is 1 by 1 plus e raised to minus x. So it's like a sigmoid shape. You can see it's like a sigmoid curve. So the maximum value is from 0 to 1 range. The next function is a linear function. So the value is f of x equal to mx plus c, which is equivalent to a line. That is m, which is represented as a slope, and c is represented as the y-intercept. And the value is ranges from 1 to -1. Another linear function, which is called piecewise linear function, which can be represented as if x, which is less than x min, which is equal to 0, and if it's in the range x min to x max, the value is mx plus c. If x is greater than x max, the value is 0. So again, the range is lying from -1 to 1. The next activation function is Gaussian function, which is equal to a normal distribution. That is 1 by sigma root 2 pi exponential of minus x minus mu the whole square by 2 sigma square. The sigma is the variance and mu is the mean value. And here you can see it's like a normal distribution, that is a Gaussian curve. The next activation function is hyperbolic tangential function, which can be represented as e raised to x minus e raised to minus x divided by e raised to x plus e raised to minus x, which is equivalent to a tan function, that is which is equivalent to a tan theta, e raised to theta minus e raised to minus theta divided by e raised to theta plus e raised to minus I theta. So it is equivalent to a tan function. So in this slide, I will discuss one problem. So the question is, we need to compute the output of the following neuron if the activation function is threshold, sigmoid and hyperbolic tangent function. Let's see how we can do the problem. So here the input and the weight value is given. Let's see how we can find. So in this slide, I'm going to explain how we can apply Perceptron network. So Perceptron is one of the famous and one of the alternate neural network. So Perceptron is an artificial neuron in which the activation function is a threshold function. So consider an artificial neuron having x1, x2, xn as the input signal and w1, w2, wn as the associated weights and w0 be the constant. The neuron is called a perceptron if the output of the neuron is given by the following function. That is the constant plus w1 into x1 up to wn into xn, which is greater than 0, the value is 1. If it is less than or equal to 0, it will be minus 1. So in this flow chart, you can see the different inputs, weight and the summation, and here we have applied a threshold function, and if your activation function is the wi into xi, which is greater than 0, it is 1. If it is less than 0, it will be minus 1. So we can implement any Boolean operation by using perceptron. So here the Boolean function of AND can be represented like this. It can be binary data or it can be a bipolar data. So bipolar means we have to consider the sign, like if it is 0 0, you have to consider minus 1 minus 1. If it is 1 1, then you can treat it as 1 1. So this is an AND function. So we can implement any Boolean function by using perceptron. Let's see the representation of x1 and x2 by a perceptron. So here the weight values are given. W0 is minus 0.8, W1 and W2. So here you can see the weights value and the different inputs can be taken from the gate. So the activation function is if wi into xi, which is greater than 0, it is 1. If it is less than 0, then it is minus 1. So we can apply here minus 0.8 in plus 0.5 into the first input plus 0.5 into x2, which is greater than 0. Then you can represent the output be 1. Similarly, for the each input, you can take the input and you can apply it here and you will get the corresponding output. So not only for AND gate, you can implement or any other Boolean operation by using percept. So let's see the different weights associated for each Boolean function. For the AND gate, it will be W0 is minus 0.8, W1 is 0.5, W2 is 0.5. For the OR gate, it is minus 0.3, 0.5, 0.5. For the NAND gate, it is 0.8, minus 0.5, minus 0.5. For the NOR gate, it is minus 0.5, minus 0.5, 0.3. But the problem is not all Boolean functions can be represented by perceptron. For example, the Boolean function x1 XOR x2 cannot be represented by a perceptron. This means that we cannot assign values to w0, w1, w2 such that the expression w0 plus w1 into x1 plus w2 into x2 takes the value of x1 XOR x2. So we can implement AND, NAND, OR, NOR gate, but we can't implement the XOR gate by using a single perceptron. So next is perceptron learning algorithm. So we have to use following notation. N is the number of input variable, Y is the output, and D is the training set of samples. Xj is the n-dimensional input vector. Dj is the output value of the perceptron. Xji is the value of the ith feature of the jth training input vector. Xj0, the bias which is fixed, that is 1. Wi is the weight of the ith input variable, and Wi of t is the weight I at the tth iteration. The first step is we have to initialize the weight and the threshold. The weight may be initialized to 0 or a small random value. The second step is for each example J in the training set D, perform the following steps over the input Xj and the desired output Tj. So first step is calculate the actual output. So how we can calculate the actual output? That is each input which is multiplied by a weight. For the bias, it is W0T into XD0. Then you have to apply an activation function over this net input. The next is you have to update the weight. So the new weight will be the old weight plus dj minus yj of t into xji. That is the expected output and the target output difference into input for all features 0 less than or equal to I less than or equal to n. And you have to repeat the step until the iteration error. So the iteration error is the difference between the actual and the desired output. So the dj minus yj of t, which is less than a user specified error threshold or a predetermined number of iteration have been completed, then you can stop the iteration. Let's see the characteristics of an ANN. An ANN can be defined and implemented in several different ways. The particular variant of an ANN is determined by the way the following characteristics are defined. The first characteristics is activation function. This function defines how a neuron's combined input signals are transformed into a single output signal to be broadcasted further in the network. And the second characteristics is network topology or architecture. This describes the number of neurons in the model as well as the number of layers and manner in which they are connected. And the third characteristics is training algorithm. So this algorithm specifies how connection weights are set in order to inhibit or excite neurons in proportion to the input signals. Next is network topology. Network topology means the pattern and structures in the collection of interconnected nodes. Larger and more complex networks are capable of identifying more subtle patterns and complex decision boundary. The power of a network is not only a function of the network size but also the way units are arranged. So the different network architecture can be differentiated by the following characteristics: the number of layers, the number of nodes within each layer of the network, whether the information in the network is allowed to travel backward. So next is how it will affect the number of layers. Here you can see only one layer. That is, here we have only input layer and output layer. But in this one, you can see the different layers, that is input layer, hidden layer and output layer. And more than one hidden layers also. Let's see the number of nodes in each layer. The number of input nodes is predetermined by the number of features in the input data. The number of output nodes is predetermined by the number of outcomes to be modeled or the number of class levels in the outcome. The number of hidden nodes is left to the user to decide prior to the training the model. Unfortunately, there is no reliable rule to determine the number of neurons in the hidden layer. The appropriate number depends on the number of input nodes, the amount of training data, the amount of noisy data, and the amount of complexity of the learning task, and among many other factors. The direction of information travel. The networks in which the input signal is fed continuously in one direction from connection to connection until it reaches the output layer are called feed-forward networks. The multi-layer feed-forward networks are sometimes called the multi-layer perceptron. The networks which allows signals to travel in both directions using loops are called recurrent networks. Let's see the different examples of different topologies of network. So first one, it's network with one hidden layer and two output nodes. The second layer is network with two hidden layers, and the recurrent network, which is a special network. You can see here the connection from the hidden layer to the input layer. So it's like a one layer is connected to the other layer. So that is called a recurrent neural network. There is a backward loop rather than the forward connection. Let's see what is cost function. In a machine learning algorithm, the cost function is a function that measures how well the algorithm maps the target function that it is trying to guess how well the algorithm performs in an optimization problem. So the cost function, which is also called the loss function, the objective function, the scoring function, or the error function. So let's see the different type of cost function in the coming slide. Let's see the different examples of cost function. The first cost function is SSE, that is sum of squared of the difference. It is calculated the squared difference between the predicted and the actual value, that is ya minus y cap the whole square. The next is MSE, that is mean square error, which can be computed as MSE is equal to 1 by n into sigma I is equal to 1 to n ya minus ya bar the whole square. Let's see one important feed-forward neural network algorithm, which is called backpropagation algorithm. And still, this algorithm is popular nowadays in deep learning or deep neural network. Still, we are using backpropagation algorithm. So, first step is initially the weights are assigned at random. The second step, then the algorithm iterates to many cycles of two processes until a stopping criterion is reached. And each cycle, which is known as epoch, and each epoch include two steps. One is called forward phase and second one is backward phase. So let's see what is forward phase. So in forward phase, in which the neurons are activated in a sequence from the input layer to the output layer, applying each neuron's weight and activation along the way. Upon reaching the final layer, an output signal is produced. And the second phase is a backward phase, in which the network output signal resulting from the forward phase is compared to the true target in the training data. And the difference between this network output signal and the true value result in an error, and that is propagated backward network to modify the weights between the neurons and try to reduce the future errors. Let's see the third step in backpropagation algorithm, that is a weight updation. So in this steps, we have to update the weight by using a method called gradient descent method. So at every stage computation, we have to calculate the error function. So error is a function of the weight. And if we plot the error against the weight, we get a higher dimensional analog of something like a curve or a surface. So at any point on this surface, the gradient suggests how steeply the error will be reduced or increased for a change in the weight. So this algorithm will attempt to change the weights that result in the greatest reduction in error. So in this figure, you can see this is a simplified model of the error surface showing the direction of the gradient. And you can see the direction of the gradient and the initial weight. So here the error treated as a function of the weight, and the whole surface which is indicated as error surface. So how we can update the weight is the Wi new, which is equal to Wi alt minus eta into dou E of dou W. So dou E divided by dou W is the gradient of E with respect to the W. So that means the rate at which E is changing with respect to the W. So this gradient can be computed as minus T1 minus output of O1 into output of O1 into 1 minus output of O1 into output of H1. So O1 is indicating the output layer, H1 is indicating the hidden layer. So it can be rewrite as the sigma of O1 into output of H1. That is the gradient of E with respect to the W. So let's see one example how we can apply backpropagation algorithm. So here you can see two input and output target 1 and output target 2. And we have two sample 1 and 2. So the first step is to initialize the connection weights to a small random value. The second step, present the first sample inputs and the corresponding output target to the network. Third step, pass the input values to the first layer. And fourth step is calculate the outputs from H1 and H2 using a logistic activation function. So your output of H1 is 0.59327 and output of H2 will be 0.5968. So in this step, we repeat this process for every layer and we get the outputs from the nodes in the output layer as follows. The output of O1 it is equal to 0.75137, output of O2 which is equal to 0.77293. The next is the sum of squares of the output error which is given by E is equal to half into the T1 minus output of O1 the whole square plus half into T2 minus output of O2 the whole square. So we already know that the output of O1 and output of O2 and T1 and T2, substitute the value, you will get 0.29836. So step 6 is we begin the backward phase, we adjust the weights. So first adjust the weight leading to the nodes O1 and O2 in the output layer, then the weight leading to the nodes H1 and H2 in the hidden layer. So the adjusted value which can be represented as W1 to W8, B1 to B4. The computation uses certain constant which is called learning rate, and here we choose the learning rate as 0.5. So in this slide you can see how we can update the weights delta O1, delta O2 and each weight and bias. So delta O1 which is calculated as T1 minus output of O1 into output of O1 into 1 minus output of O1. So we already know the values. Similarly, we have to update W5, W6, W7, W8. So W5 mu is W5 plus learning rate into delta of O1 into output of the hidden layer. Similarly for W6 and for the W7 and for the W8. So for this W7 and W8 which is in O2, that is a second output layer. So the second output layer can be calculated as T2 minus output of O2 into output of O2 into 1 minus output of O2. So substitute the value and you need to update the bias also, that is B4 plus is B4 plus eta into delta of O2 into the constant value 1. So you will get the B4 also. So in this slide I will explain how you can adjust the weight in hidden layers, that is delta H1 and delta H2, and how we can update the weight and bias. So let's see, delta H1 can be computed as delta O1 into W5 plus delta O2 into W7 into output of H1 into 1 minus output of H1. So substitute the value, we will get delta of H1 as minus 0.00877. W1 mu is equal to W1 plus eta into delta H1 into I1. Similarly, W2 and the bias. The second one, the second hidden layer delta, that is delta O1 into W6 plus delta O2 into W8 into output of H2 into 1 minus output of H2. And we have to update W3, W4 and the bias value. In step 7, set the different weights value, that is W1 is equal to W1 plus, W2 is equal to W2 plus, similarly for all the weights and bias. So our aim is choose the next sample input and the corresponding output target to the network and repeat the steps 2 to 6. Finally, the process in step 7 is repeated until the root mean square error of the output, that's output error, is tried to minimize. So we can stop this iteration. In this slide, I'm going to explain what is backpropagation algorithm. So let's see some of the notation. That is, M is number of layers, Nj is the number of neurons, and xp1 to xpn0 is the training sample, and tp1 to tpnm is the output, and op1 to opnm is the actual output, and yji is the output from ith neuron in layer J, and wjik is the connection weight from kth neuron in layer to the ith neuron in layer J, and delta J is the error value associated with the ith neuron in layer J. So first step is initialize the connection weight into a small random value. Then second step is present the pth sample input vector of pattern xp is equal to xp1 to xpn0 and the corresponding target is tp1 to tpn. So third step, pass the input value to the first layer. For every input node I in layer 0, perform y0i which is equal to xpi. The fourth step is for every neuron I in every layer, we have to find the output. So for that, we need to apply the activation function over the net input. That is yji which is equal to f of sigma k is equal to 1 to n of j minus 1 into y of j minus 1k to wjik. Then here the activation function is 1 by 1 plus exponential of minus x. Finally, you have to obtain the output value. For every output node I in layer M, perform OPI is equal to YMI. Let's see the step 6. So here we have to calculate the error value for every neuron I in every layer in backward order. For the output layer, the error value which is equal to delta mi which is equal to ymi into 1 minus ymi into tpi minus ymi. And for hidden layer, the delta ji which is equal to yji into 1 minus yji into sigma k is equal to nj plus 1 into sigma of j plus 1 into w of j plus 1 into ka. The weight adjustment can be done for every connection from neuron k in layer j minus 1 to every neuron j in every layer I. So wjk is equal to wjk plus sigma into delta ji into yji, where eta represent the weight adjustment factor normalized between 0 and 1. The last step is the action in step 2 through 6, which will be repeated for every training sample pattern and repeated for these sets until the sum of the squares of output error is minimized. So in this video, we have discussed what is backpropagation algorithm and what are the different types of activation function, what is neural network, what is the difference between neural network and biological neural network, and more details about the architecture of neural network and different types of neural networks. So thank you all for watching this video.